In this video, we're going to start chapter 13. And chapter 13 is on chemical equilibrium, which is a concept that we're going to use a lot this semester. So we introduce it in chapter 13, but then we're also going to use equilibrium in most of the rest of the chapters. So a lot in chapter 14, 15, a little bit in our thermodynamics chapter also. So it's a very important concept that we will be using a lot. So chemical equilibrium. So essentially the deal is that not all chemical reactions actually go to completion. So reactants don't always go just to products. Products can actually go back to reactants. So at any given point, we could have both a mixture of reactants and products. Essentially, many reactions occur both in the forward and reverse direction. So not all reactions go to completion. Right, many reactions occur in both the forward and reverse directions. So I could have A going to B. That's how we would normally look at a chemical reaction, right? And it is going to completion. A is forming B. So when the reaction is essentially done, I only have B, right? A has disappeared, B has appeared. But several reactions actually go in both directions. So we're not just forming B, we're also forming A. So many reactions actually go in the forward and reverse directions. This doesn't necessarily mean they're at equilibrium. Be really careful. Just because a reaction is reversible, which is what this is, right? It goes in both directions, doesn't mean we're at equilibrium. When the rates in the forward and reverse direction are equal, then we are at equilibrium. And this is a really important concept. So just because it's going back and forth, right? Just because it's reversible doesn't mean we're at equilibrium. It just means it's reversible. When the rates in both directions are equal, we are at equilibrium. That's what the equal in equilibrium means, right? We have equal rates in the forward and reverse direction. So when the rates in the forward and reverse directions are equal, the reaction is said to be at equilibrium. That's impossible to read, sorry. Abbreviated EQ. So often I'll just use an EQ for equilibrium. So again, really important, right? The rates in the forward and reverse direction are equal, then we're at equilibrium. So just because it's reversible doesn't mean we're at equilibrium. Those two rates would have to be equal. Note, also important, right? The concentrations of A and B aren't equal. It's the rates that are equal. So we don't have to have equal amounts of reactant and product, right? My concentrations do not need to be equal. My rates need to be equal. So the concentration, right? We'll use these brackets again for concentration. So the concentration of A and B, let's actually write that a little bit better. I will write it out. This is important. The concentration of reactants and products does not need to be equal. Right? Only the rates. So be really careful. That's a really common misconception, right? We think equilibrium, we think, well, A and B have to be equal. they do not, right? Only the rates in which you're forming B and the rates at which you're forming A have to be equal. I know I'm beating this to death, but it's really important. It is a dynamic state. So what we mean by that is the reaction is still occurring. So even when we're at equilibrium, we're still forming A, we're still forming B, but because we're forming them at the same rate, there's actually no net conversion of reactants and products. It actually looks like we're not forming anything. It kind of looks like it's just sitting still, but it's not. It is dynamic. We are forming A and B. It's just that since we're doing that at the same rate, it looks like it has stopped. So it is a dynamic state, right? It appears that the reaction has stopped. RxN being my abbreviation for reaction. But it has not, right? There is no net conversion of reactants to products and vice versa, right? Products to reactants. But both reactions are still occurring. So again, it looks like nothing's happening, right? My concentration A and B are constant. They're not changing because I'm forming A at the same rate that I'm decomposing A, right? I'm forming B at the same rate that I'm decomposing B. So it looks like nothing's happening, but it is dynamic. My reaction's still occurring. It's just that there's no net change in my concentrations. We can establish equilibrium starting only with reactants, only with products, or with a mixture of the two. So equilibrium can be established. So EQ again for equilibrium. Starting with reactants, products, or both. So if you were in lab and you just had reactants, you would form products. Products would go back to reactants. When those rates are equal, you would have equilibrium. You could start with just reactants. Those reactants would form products, right? These are reversible. Those products would go back to reactants. When that happens at the same rate, we're at equilibrium. We could start with a little bit of both. When they're going back and forth at the same rate, again, we're at equilibrium. At a given temperature, the ratio of reactants and products, again, is going to always be the same, right? Because there's no net conversion, right? It appears that it stopped, but again, those rates are equal. An example for us, I'm going to have dinitrogen tetroxide, that's hard to say, N2O4, and it's a gas. It's forming 2 nitrogen dioxides, also a gas, and then that's going back to form N2O4. When the rates in the forward and reverse direction, we can say that we're at equilibrium. Oh, let's talk, before I move on to my actual example while I'm thinking about it, let's talk about these arrows real quick. It is important. So just a normal reaction arrow, just a straight reaction arrow, right, would just be in one direction with 2 barbs. If your reaction is reversible, we do use 2 separate arrows going in an opposite direction. If we are at equilibrium, and we know for sure that we are at equilibrium, it's common to actually just use 1 barb. I still tend to use 2 because sometimes we're talking about establishing equilibrium and we're not there yet. So a lot of times you'll see the arrows this way, and that's okay. But if we wanted to be really technical and correct about it, we really only want to use these one barbed arrows when we know for sure that we are at equilibrium. So if we're talking about a reaction that's reversible and we just aren't at equilibrium, but it's still reversible, right? Remember, something can go back and forth without being at equilibrium. Then we use arrows that have the 2 barbs on them. Do be careful for a resonance arrow. Do not use this. A resonance arrow is something entirely different. You'll use this in organic. So 1 arrow with 2 sides means something different. So do not use that one. We're not going to be using that in this course at all. So for us, don't use this. If you do use it though, however, I will mark it as incorrect because we are not going to be using resonance arrows to show reversible reactions. If you want to use either this one or this one, that's fine. Again, there is a difference between the two. If we're at equilibrium, feel free to use the 1 barb. If it's just reversible and you don't know for sure, use the 2. I tend to use both. Okay. So the way that I wrote this, essentially what we're saying is that we just have a reversible reaction. When the rates are the same, then we're at equilibrium. So I'm just going to make a couple graphs. Remember when we were looking in kinetics, right? If I was to graph my concentration versus time, right? If I start out with reactants, over time, it decreases, right? And we said that the rate changes as time goes on, right? It tends to slow down. The slope to my tangent line at a given time, right, isn't as steep, right? It's a smaller slope. It's a slower rate as time goes on. If we were looking at products, we start low because we start with any and we increase, right? Because products up here over time. So if I wanted to look at a graph for these two, I'm just going to move this stuff out of my way because I want it next to the reaction here. And we had said that we can start or establish equilibrium starting with reactants or starting with products. So again, concentration measured in molarity versus time. So if I wanted to start out with N2O4, right, its concentration would decrease. My concentration of NO2 would increase. So I'm going to have a line kind of coming down. I'm going to have another one coming up. This one that's decreasing is my concentration of N2O4. This one that's increasing is my concentration of NO2. And then at this point where they're straight, right, where it's kind of leveled off, I can draw a dotted line here. And the way I drew my graph, it actually probably goes, I'm going to cut right through my labels, but I probably would have, I don't know, put it somewhere around here, right? This is where this line becomes straight. This is where I'm at equilibrium. So everything to this side of that dotted line is where we've established equilibrium, right? My concentration has kind of leveled off. My rate, I should say, has leveled off. Remember, it's still a dynamic, it's still occurring, it just looks like there's no net conversion. So we would say equilibrium has been achieved. If I wanted to look at it starting with, that's a crazy crooked line, starting with NO, so this is starting with N2O4, starting with NO2, again, concentration versus time. So this time I'm going to have NO2 increase. I kind of wanted to make that more, sorry guys, I kind of wanted to make that straighter. So this would be my concentration of N2O4. Right? It's up hereing this time because I'm starting with NO2, right? NO2 is, you can think of it essentially as my reactant, right? I'm looking at the reverse direction. So my concentration of NO2 is going to decrease. And then again, kind of where these have leveled off, that's where we've achieved equilibrium, right? So kind of the point here, and I'm sorry if this is confusing, but we're still going to call the things that we write to the left of my reaction arrow reactants. I'm still going to call these products, but we are going to look at the reaction as being reversible. So if I'm starting with this, which is what I'm doing here, I'm really thinking of that as a reactant. I'm still going to call it a product just because it's written on the right side of that arrow, but it's what I'm starting out with. So it's going to start up high and it's going to decrease as time goes on because that's what I'm starting out with. I'm not starting out with N2O4, so it's starting low, and then its concentration increases as time goes on. And then where these rates have leveled off, right, everything over here, we would say we've established equilibrium. This first one is closer to kind of what we've looked at, right? I'm starting with this, so that's my traditional reactant. Its concentration decreases. This is my traditional product. Its concentration increases. And then again, where my rates have leveled off here, that's where we've established equilibrium, right? Those rates are equal. They're both straight lines. Do note that my rates are different for N2O4 and NO2, right? We learned in chapter 12 that those coefficients, right, have an effect on my rate. For every one of these, I have to form two of those, right? If we were to write our rate expression, it would be the change in concentration of N2O4 over the change in time, and I would have a negative sign if we're starting with that one, being equal to the change in the concentration of NO2 over 2 times the change in time, right? I would have a 1/2 in front of that. So do note that my rates, right? I didn't put a scale on there, but these rates are going to be 1/2, right, of this, right? It's smaller because of this coefficient from 2, right? We can't forget what we learned in chapter 12. Equilibrium reactions do follow what's called a law of mass action, also known as an equilibrium constant expression. So equilibrium equations follow a law of mass action, which I hardly ever use that term. So our law of mass action is also called, and this is what I use more often, an equilibrium constant expression. Sometimes just shortened to equilibrium expression. So that's really what you're looking for. So either equilibrium constant expression or equilibrium expression. And I'll show you what that is here in a minute. Also called the law of mass action. I don't use that one so much, every once in a while, but this is really what we're looking for. So I do want to show you where it's coming from. So I'm going to look at a generic reaction. So I'm going to have A moles of A plus B moles of B, forming C moles of C plus D moles of D. This is a reversible reaction, so I can have C and D going back to A and B. I'm going to write my rate laws for these. So in the forward direction, so I'm going to put an F here for forward, my rate law, lowercase k, and we are going to assume that it's a one-step mechanism. So if we assume that, then this is my rate determining step. Remember, we can actually take the concentration of our reactant and raise it to a power equal to our coefficient for the rate determining step, right? Only for rate determining steps. But if it's a one-step mechanism, this is my rate determining step. So this would be my rate law in the forward direction. I am going to put an F subscript on my rate constant just to keep it straight from my rate law for the reverse direction. So if we were going backwards, right, these I'm going to think about as being my reactants. I'm going to think about this as being my product, right? We're going in this direction. So when I write the rate law for this, we're starting out with C and D. So that's how I'm going to write my rate law. Again, we're assuming a one-step mechanism. So this is my rate determining step, so I can do this. If we are at equilibrium, remember when we're at equilibrium, my rate in the forward direction is equal to my rate in the reverse direction, right? That's our definition for equilibrium. So at equilibrium, rate F is equal to rate R. So using whatever property that is for math, whose name I forget, right? If this equals this and this equals this, and these two things are equal to each other, right? Then these are also equal to each other. So I'm going to rewrite that. Because we're at equilibrium, I am going to put EQs after my concentrations to specify that we have to have equilibrium concentrations, right? If they're not equilibrium concentrations, then this isn't going to work for us. So that's what that additional little EQ means for us, right? At equilibrium, I have equilibrium concentrations, and my rate in the forward direction is equal to my rate in the reverse direction. So we start the reaction, right? Remember, we can start with either reactants or products. So I could start with A and B. I could start it with B and C and D. I could start it with all of those. We let time go on a little bit, and eventually my two rates are going to be equal. My concentrations then are my equilibrium concentrations, and this statement is true. I'm now going to rearrange this to get all of the concentration terms on one side and my rate constants on the other side. So rearranging this a little bit, I'm going to have KF over KR, and then that's going to be equal to my concentrations of C and D. Again, remember they need to be equilibrium concentrations, not any old concentrations. And that's over A and B concentrations. And then we're going to just do one more thing. I'm going to take this and we're going to set that equal to our equilibrium constant. So that's going to be equal to a capital K. This is why I was reminding you so often to use lowercase k's for rate constants. A capital K is going to be my equilibrium constant. So this is my equilibrium constant. And then this entire thing, let me get rid of this box. This is my equilibrium constant expression, or my law of mass action. Oftentimes you're going to see a subscript on your equilibrium constant. It does vary, that subscript, depending on what it is that we're talking about. So I'm going to put a C right now because I'm defining this expression in terms of concentrations. In chapter 14, we're going to have A's and B's for acids and bases. In chapter 15, we're going to have SP's for solubility product constants. In this chapter, we're also going to have P's if we're defining it in terms of partial pressure. But regardless of what little subscript you see after it, a capital K is my equilibrium constant. Sometimes you'll actually see an EQ also just for equilibrium, kind of the generic one. So kind of if we look at what we have, my equilibrium constant, it's equal to the concentration of my products, right? C and D were my products, raised to a power equal to their coefficient over the concentration of reactants raised to a power equal to their coefficient. That gives me my equilibrium constant expression. And Kc is also equal to, right, my rate constant in the forward direction divided by my rate constant in the reverse direction. So if we knew the equilibrium constant in one of my rate constants, we could calculate the other rate constant. If we knew both rate constants, we could calculate the equilibrium constant, and so on. Again, be careful not to get lowercase k's and capital K's mixed up. It is important because they are representing different things, and I have them here in the same equation. Using the example that we had previously, I had N2O4 going to 2 NO2s. These are both gases. And then this was reversible. I didn't leave myself any room. So eventually it's going to reach equilibrium. So we are going to write the equilibrium constant expression. So again, it's just going to be concentration of products over concentration of reactants, each raised to a power equal to the coefficient. And then I'm going to set that equal to my equilibrium constant. So my expression, Kc, is going to be equal to the concentration of NO2, and this does have to be at equilibrium, otherwise it's not equal to the equilibrium constant. We're going to actually have instances in this chapter where I have concentrations that aren't at equilibrium, and I'm going to set them equal to something different. I'm going to have a different constant. Because I have 2 moles of nitrogen dioxide, I'm going to raise that to the second power. And then that's going to be over the concentration of N2O4, also at equilibrium. And then that's raised to the first power because I have 1 mole. So this would be my equilibrium constant expression for this reaction. So again, concentration of products over the concentration of reactants, each raised to a power equal to their coefficient. For heterogeneous reactions, and these are reactions where I have more than one different type of state of matter. So some of my reactants could be gases, some could be solids, liquids, or aqueous solutions. So for heterogeneous reactions, we are actually going to exclude pure solids and liquids from the expression. Essentially, the concentration of something that's a pure solid or a pure liquid is not changing, right, as the reaction proceeds. If it's, water, for example, a pure liquid, it's always 100% water. I might have less water, right, if it's a reactant, or more water if it's a product as the reaction goes on, but it's always going to be 100% water, right? Its concentration isn't going to change. So solids and liquids that are not in solution are going to be excluded. So when you're writing your expressions, if it has an S or an L after it for its state of matter, don't include it. We're only going to include gases. I know gases, right, because we can have mixtures of gases because they're expandable, they can contract, right? Its partial pressure can change. We do include those. So only include gases and solutions in the expression. Couple examples for us here. I have silicon tetrachloride, and it is a gas. I'm reacting it with 2 hydrogen, also a gas. We're going to form silicon, which is a solid, plus 4 hydrochloric, in this case, because it's a gas, hydrogen chloride molecules, right? It's only hydrochloric acid when it's an aqueous solution. Because this is a gas, hydrogen chloride. And we're going to write our expression for this. So again, we're only going to include gases and solutions we're going to exclude or not include solids and liquids. So when I write the expression, we're going to omit silicon from my expression, right? Because it's a solid. So Kc, concentration of products, this time only HCl. I have 4 moles, so I'm going to raise it to the 4th power, over the concentration of my reactants. Both of them are gases, so we can include them. I have 2 moles of hydrogen, so I am going to raise that to the 2nd power. Another example for us, let's have 2 hydrogen, also a gas, plus oxygen gas, and I'm going to form 2 water, which is a pure liquid. So again, we're going to write our expression for this. It's going to be, again, concentration of products over reactants raised to powers equal to their coefficients. However, right, my only product I'm going to not include. So I'm actually just going to have 1 on top over the concentration of hydrogen raised to the 2nd power, because there's 2 moles, multiplied by the concentration of oxygen raised to the 1st power. So again, only include gases and solutions in our equilibrium constant expression. We can define equilibrium constants in terms of partial pressures, and we're going to use Kp when we do that, right? The C in Kc, right, that was representing concentrations. So when I wrote these expressions, right, we had these brackets representing my molar concentration. Kp is going to be expressed using partial pressures. Remember, if we have a mixture of gases, the individual pressures, or the pressures exerted by the individual gases in that mixture, are my partial pressures. That would have come from Dalton's law in your gas chapter from 150, 151. So expressed, which I can't spell, using partial pressures instead of concentrations. So if I wanted to, let's actually just do the couple that we've done already. So I'm going to go back up to this equation. If I want to write Kp for that, and let's copy it down, it'll be easier. Right? I'm going to do it a very, very similar way. It's still going to be products over reactants, still going to be raised to a power equal to its coefficient. It's just that instead of putting brackets for molar concentration, I'm going to do a P for partial pressures. So Kp is going to be equal to the partial pressure of NH3 raised to the 2nd power over the partial pressure of hydrogen raised to the 3rd power multiplied by the partial pressure of nitrogen, again raised to the 1st power because there's 1 of them. And just like our concentrations, right, up here, all of these needed to be at equilibrium, right? If they're not equilibrium concentrations, then I'm not going to solve for my equilibrium constant. The same thing here. My partial pressures need to be at equilibrium. If they're not at equilibrium, I'm not solving for an equilibrium constant. I'm solving for something different. So expressed using partial pressures, again, key at equilibrium, right? We're not going to solve for an equilibrium constant if we're not using equilibrium concentrations or pressures. If I wanted to write Kp for this one, same sort of thing. Water doesn't get included, but then I would be using the partial pressure of hydrogen at equilibrium raised to the 2nd power multiplied by the partial pressure of oxygen raised to the 1st power. So again, setting it up very similar, it's just substituting molar concentrations for partial pressures. I am only going to use Kp when everything that's included is in the gas state. If some are gases and some are aqueous solutions, I am going to have to use Kc. And that's probably worth writing down. So we can use Kc when we have, let's actually say, can use when we have gases and or solutions. So it can be just gases, it can be just solutions, it can be both. Kp can use only, let's say can only use when we have gases. And if you're thinking, well, what about the example I just did? Which I know I would be, right? This one right here, right? We had a liquid. The liquid is not part of my expression. So if you wanted to add a clarifier, can only use when gases and or solutions are the only things that are part of the expression. Kp can only use when we have only gases as part of our expression. Again, we're really always just going to be ignoring solids and pure liquids. We do have an equation that relates Kp to Kc. So if you know Kp, you can calculate Kc or vice versa. And our equation for that is that Kp is equal to Kc multiplied by R, which is our gas constant, times T, which is our temperature, right? It's a capital T. And then RT is raised to the delta N, which I will define here in a second for you. So R is going to be my gas constant. Remember on the back of your periodic table on your equation sheet, you have two versions of the gas constant. This time we want this one, so 0.0206 liters atmospheres per mole Kelvin. For our temperature, it does need to be in Kelvin, right? Because my gas constant is in terms of Kelvin, my temperature also needs to be in terms of Kelvin. And then delta N is going to be the number of moles of gaseous products minus the number of moles of gaseous reactants. So the number of moles of products that are gases, right, minus the number of moles of reactants that are gases. Again, everything that's part of the expression, if we're using Kp, does need to be in the gas state, right? We can only use Kp when we have gases, all being a keyword. So let's do an example here. So we're going to determine my equilibrium constant in terms of concentrations and Kp for the following reaction. So my reaction, 3 hydrogen plus nitrogen, those are both gases, forming 2 ammonia, which is also a gas. And then we're given equilibrium concentrations. And then I'm just going to list them here. So for hydrogen, it is 0.104 molar. For nitrogen, 0.554 molar. And for ammonia, 0.418 molar. And then this is everything we're given. This equation, which we will need, is on your equation sheet. So you would be given everything that I have here in blue plus that equation. In fact, let's just copy that down so we have it on the same screen here. We don't need it for a little bit yet though, so we'll paste it down a little bit lower. Okay, so I'm gonna solve for Kc first. The reason we know to do that, right, is we're given our concentrations, right? If we were given partial pressures, we would solve for Kp first and then use that equation to get Kc. But because I'm given concentrations, we're gonna solve for Kc first, then use that equation to get Kp. So the first thing we need to do is actually set up our expression. So we're going to write our equilibrium constant expression for this reaction. Once I have that expression, we will plug these concentrations into the expression to solve for Kc. So my expression, right, they're all gases, so I'm not going to exclude anything, right? If I had a solid or a liquid, we wouldn't include it, but these are all gases. So I'm going to have the concentration of ammonia raised to the second power, because there's 2 moles, over the concentration of hydrogen raised to the third power, multiplied by the concentration of nitrogen raised to the first power. Now that I have those, I'm going to plug my concentrations into that expression. So ammonia, 0.418, we do need to square that, over 0.104 cubed multiplied by 0.554. So I'm going to grab my calculator. I would highly recommend you do the same. If you have to hit pause, please do. And I got 280.377. I do need 3 significant digits. The 280.3 means that it's going to round to 280. My problem right now, however, though, is that if I have a trailing 0 and no decimal point, that trailing 0 is not significant. So if I write 280, I actually only have 2 significant digits. So I am going to put this into scientific notation so I can express the right number of significant digits. If you're wondering what I'm doing with units, I did ignore them completely. I'm going to throw them in here just real quick so you can see it. This would be molar, this would be molar, and then I have a molar here. So essentially what I have for my units right now, I have molar squared on the top, I have molar to the 4th on the bottom. So my units right now would be 1 over molar squared, or molar to the -2. The units for equilibrium constants are going to vary depending on that expression, right? Here it's molar to the -2. If we scroll back up a little bit, right, and look at different ones, here it would be 1 over molar cubed. This one I would have, well, just molar, right? It's going to vary depending on what my expression is. It is commonplace, and this is really the only time that you guys can do this, to exclude units on equilibrium constants. So it's perfectly acceptable and standard to not include units. Do be careful though, it does have units, we're just not showing them. And that is entirely different than saying it doesn't have units. Right? If you were answering a multiple choice or a true and false question, and I said equilibrium constants do not have units, the answer is false, right? It has units, we're just not going to show them. So units are not typically shown when expressing equilibrium constants. So again, usually you're going to lose points if you exclude your units. Right here, you're not. It is standard to not show units. So units are not typically shown when expressing equilibrium constants. Again, do know they have them though, even though they do have units. So they have units, we're just not going to show them. If you want to show them, go for it. It's not incorrect. Just make sure that you show them correctly if you're going to, right? If you show units and you show the wrong units, it's actually wrong and I will take off. So it's probably better to just not show them. So units, we can actually ignore them. I'm in such the habit of ignoring them when I did the problem, right? I didn't even write them there originally. Of course, I'm erasing the whole thing. But I had just written the values without those units. Okay, next part, moving on, right? We're now going to take this value and we're going to use this equation and we're going to calculate Kp. I do need delta N. That was the number of moles that are gas products minus the number of moles of gas reactants. So if I go back up to my equation here, on the product side, I have 2 moles. On the reactant side, I have 3 here. There is 1 here, so that gives me 4 moles. So I'm going to have 2 minus 4, so that's going to be a -2. So Kp is going to equal to Kc, the value we just solved for, multiplied by my gas constant, I am going to end up ignoring units again when I express Kp because it is an equilibrium constant. The reason I'm writing them here in my gas constant is I'm going to use this to remind myself that my temperature needs to be in Kelvin. And I might have actually forgot to give you a temperature. I did. Sorry guys, at 25.0 degrees Celsius. So 25 is considered room temperature. I am going to add that to 273, get 298. I can do math. Kelvin, capital K. And then be careful on this math, right? It's only RT that's raised to delta N. So I do need to throw some brackets around here and then raise this to the -2 power because that's what we got for delta N. So if you want to grab your calculators again, it would be a great idea. And I got that Kp is equal to, that's a 0.468. Again, it has units, we just don't need to include them here.